It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappening? Today, we're going to learn about the history of light. Like everything we've learned in this class, it all starts with Isaac Newton. And Isaac Newton started thinking about light. And this started in 1666 when Isaac Newton self-quarantined himself during the bubonic plague. And one question he had was, how do we see? And because he didn't have a lot of tools with him, he had to use himself to test out his theories or thoughts on how we see light. One idea was that we saw light we saw images based on the pressure against our eyes from light. So as light was coming in, it would exert some sort of pressure on the back of our eyes, which would allow us to see an image. So what he did to test this out was he would take a bodkin needle or a sewing needle, he'd pull his eyelid down, and then shove that needle in his eye, press against the back of his eye to see if that pressure would allow him to see images. Oddly enough, it turns out that didn't work. So the pressure does not allow us to see things, obviously. So pressure against our eye. His next thought was maybe we just imagine what we see. So he said, if I gather a lot of light inside my eye and go stare at a wall, which is probably what we're doing all day, maybe I could imagine images. So the best way he thought to gather a lot of light was to stare at the sun. So he'd go outside, stare at the sun for as long as he can. Please don't do this. And then he would go inside a dark room, stare at that wall, and see if he could make up any images. And all he saw was just green dots floating around, so just typical things that you'd see in a dark room. I think he did this multiple times. Eventually he realized that, oops, this probably isn't such a good idea, so maybe I should lock myself in the basement for around 3 days without any lights and hope that my eyes could heal. So his next thing was he stared at the sun. And both of these were to see or determine how we see. So to test how we see. Newton put that on the back burner for a little bit, but the next thing he wanted to do is determine what is light. Is light a particle or is light a wave? He recalled one day he was sitting out in his office and a couple of people were playing tennis, and he noticed if they struck the tennis ball a certain way, it would cause the tennis ball to curve. And he thought that, well, I know that light, unlike sound, doesn't curve around corners. Therefore, we know that sound is a wave which can curve around corners. And since light can't curve around a corner, light must be a particle. And he called this particle a corpuscle. Let's first put down that Newton was watching tennis. We don't have to capitalize tennis. Notice that the ball curved. And even though the ball is in the shape of, we could say, a sphere or particle, he didn't think that the curving of the ball is what allows light to be a particle, but the idea that a ball could curve around a corner, sound, which is a wave, could curve around a corner, but light itself cannot curve. So therefore, since light cannot curve, and sound can, which is a wave, light must be a particle. Or corpuscle. Now, what Newton said was causing the curve of the tennis ball was the air pressure being different on top of the ball versus below the ball. And this was later discovered in the 1850s, and it's named after the person who discovered it, not Isaac Newton, but a person named Magnus. And this is the Magnus effect. I'll link a video down below of a basketball displaying the Magnus effect when it's dropped a great distance. Now, this thing that was impinging against the tennis ball, Newton called ether, and he mistakenly said that light must travel through ether or a medium, which is not true, and we'll learn about that later. Just like everything that Isaac Newton said, he always had an enemy. We know that his enemy was Robert Hooke. And Hooke decided to take the opposite path, and Hooke said that light is a wave. And there were arguments back and forth between Newton and Hooke as well as the Royal Society, and they settled on that because Newton has more prominence, we're going to say that light is a particle or a corpuscle. However, it's a lot easier to treat light as a wave. So for the next 200 years or so, scientists treated light as if it were a wave, even though they believed it to be a particle. Oops. It wasn't until 1905 that the debate was settled, and Albert Einstein said that light is a photon. And a photon, all it is a massless bundle of energy. And we'll talk more about this when we get into modern physics. However, the debate isn't settled there. Shortly thereafter, is determined that light is neither a particle nor a wave, although it behaves a little bit like a particle and a little bit like a wave. And we'll talk more about that again when we determine what the heck light is and how does it behave. So let's now talk about the history of the speed of light. So the speed of light. And in this case, we're going to go one person back to Newton's predecessor, and that's Galileo. And he wanted to measure the speed of light. And he did what the most obvious thing to do is he said, let me get a really long hallway and time how long it takes light to go from one end, bounce off a mirror, and back to the other end. Obviously, he didn't have stopwatches or flashlights back then, so he used a candle, a mirror, and a long hallway to measure the speed of light. And as you would imagine, if you've ever seen light, you could tell that it travels really fast. So he was unable to determine the speed of light based on the short time it takes light to go back and forth. So the next person in 1675 to come up with an idea, or to accidentally come up with an idea to determine the speed of light, was an astronomer named Olaus Rømer. And he was observing Jupiter's moon Io, or Io. And he noticed that as Earth was moving away from Jupiter, this is moving away from Jupiter, that the time for Io or Io's orbit around Jupiter was about 22 or 20 minutes longer. So he is kind of puzzled by this fact that it took a longer time for Io to orbit Jupiter based on the idea that Earth was moving away from it. So the first thing he did was he contacted Isaac Newton, and he wondered if maybe Isaac has some miscalculations with gravity and how long it should take Io to move around Jupiter. And of course, Isaac Newton, being Newton, said, "No way. I do not have any miscalculations. It is what it is. But maybe there's something else going on here. Maybe because Earth is moving away from Jupiter, it's going to take a longer time for the light to reach us, and based on its distance, it's going to take about 20 minutes longer." So they did some rough estimations in terms of the time difference and the distance, and they ended up getting about 3 times 10 to the 8th meters per second for the speed of light. A very close number, not the exact, but given their uncertainties, they got a very accurate number. So it wasn't until in the 1880s that an even more accurate or precise number was determined. In this case, Albert Michelson, of the famous Michelson and Morley experiments, in which they sought out to determine ether, and they failed to do so, but by failing to do so, they proved that ether didn't exist. But for this experiment, Michelson said, well, let me do something similar to Galileo, but across a much greater distance. So what he did was he set up an 8-sided mirror, or an octagonal mirror, and this was, and this was on Mount Wilson, so up a huge mountain. And this mirror was 35 kilometers away from a telescope. And the idea was that light would be hitting the mirror, and if the mirror were spinning at a constant rate, then while Michelson was looking at the telescope, he would see flashes of light every certain amount of time. So if he knew the distance that the light traveled, it's going to go back and forth, so it would be 70 kilometers, as well as the time in between flashes, he was able to determine the speed of light. And what he got for this speed was 299,920 kilometers per second. And he won the Nobel Prize for this in 1907 for determining the speed of light. Now in Regents physics, we're going to say that the speed of light abbreviated with lowercase c is 3.00 times 10 to the 8th meters per second when it's in a vacuum. And we'll see when it goes through different materials that the speed could change based on a few circumstances. I hope you enjoyed this little history lesson. If you did, please like and subscribe, and I'll see you next time. See ya.